All right, so here we are over in EES, and I'm going to make these, I'm going to make the file a little bit bigger here so you can see a little bit larger. So let's maybe take this up to 12. Let's see how that looks. All right, so hopefully that's big enough on your screen. And we'll talk about all these things here in a minute. All right, so what I've done is I've just taken the example 3-4 A and B, and I just wrote the equations down here, which is just what you get from summing the moments and summing the forces. And so the beauty of this is we can just enter these equations into EES, and it automatically solves for the unknowns. So we can give it a distance. In this case, we're giving it a distance along the beam of A. We give it the distributed load here of 10 pounds per inch. And this is actually pounds force per inch. And we define these different functions, okay? So we define this function impulse, SF, impulse singularity function, and it takes x, which is where you are, and A, which is where you are concerned about. So if A is equal, you're at the first reaction on the left-hand side. If A is equal to 0, okay? So this is the unit impulse function. Okay, that's this one raised to the -1, and that's what we use for point loads in the loading function. Okay, now these functions change if we're using them in shear moment. The functions are the same, but I'm talking about them here with respect to the load function. Okay, then I have the step SF here, and it is that function that's raised to the 0 power. Okay, my VPN keeps connecting and disconnecting. So make sure you save often. Really not sure why it's doing that. Okay, so hopefully I fixed that annoying pop-up. So make sure you save often, just in case you just get disconnected. All right, so here we define the impulse function. Now, if you go back to the slides, what that is this is the pulse function here, all right? And it's also this function here. This is the load function here. So this is the that's this function here for a load that's applied at A. And then down here I have this step function here, and what I'm saying is if the difference between X and A is less than 1,000th, 1,000th of a unit, then I say that it's just equal to 1. Otherwise it's 0. So it's only really that load is just defined there in that interval between, like, minus 0.0001 and 0.001. So pretty much right at 0. So if I'm right at 0, then I have this function will just return a 1. Okay, so I define the function by saying function. I name the function, and then I name the parameters that I'm going to pass. I say that if the difference in those parameters, is the absolute value between them. And if that difference is less than 0.001, then I say that it's 1. Otherwise, I say that it's 0. So anytime we call this function with X and A, it's going to implement that singularity function. Okay, so we do the similar thing here for the steps. But you can see here, this is defined when X is equal to A, essentially. This is defined when X is greater than A. Okay, so then if it's greater than A, it's just equal to 1. this is the ramp function, and it says that if x is greater than a, that the ramp's function is equal to x minus a, okay, instead of 1. So this linearly is going to go up as a function of x. And then we have the parabolic function that is, if x is greater than a, then it's equal to x minus a times x minus a. Okay, so it's the squared term. Okay, so if we solve this here, oh, we have too many variables. So in this case, I commented out x where we wanted to evaluate it. So we can say, we can pick a value to evaluate x and then find the load. If I do that, then it gives me the load. And I can double check this with the equations, and you can see a is where that load starts. That's from that problem definition here. So I said the load starts here at 4 inches. Okay, so I say a is equal to 4. And then in this case I say x is equal to 4. I can say x is equal to 0, and what I'm doing is I'm solving at different points on the beam. So when x is equal to 0, the reaction at 1 is 18, and the reaction is 2 is 42. It shouldn't make any difference. If I say x is equal to 5, I'm just calculating things. So we have the same reaction forces, of course, as we'd expect, but our shear changes and our bending moment changes depending on what x we put in. So one of the things that we need to be able to do is plot these things, and you can see what's going on in the functions as well with the parameters that are passed to it. So we want to be able to plot these, and so in order to plot them, you still have to have the same equations and same unknowns. And for EES, what we can do is we can comment out x there, and then we can come up here to this new parametric table button. So if we connect this or click this, then we get all of the variables. Okay, so this gets all the variables in the equation, and so we need an independent and dependent variable. So here we can pick x and the shear v that we've defined, or let's pick the load q. Actually, let's pick the load q, the shear, and the moment. We'll add all of those, and I've already done that over here, but I'm going to walk you through the steps. We'll call this table example table from this is 3-4a. We'll hit OK, and then we have this other table. We have this table that's put in here. Now, because we commented out x, in order for us to solve the table, which is basically going to put an independent variable in and then solve all for the dependent variables, then we can do that. So we can come here and we can put our x values in. So I want to start at 0, and then I want to go all the way to the end of the beam, but I want to go all the way to the end of the beam in 0.01 increments. So I think I need 1,001 elements. So I can put that in there, and they say, you want to add 900? Yeah, I want to add those many rows. Double check, make sure we go all the way to 10. That's the length of the beam. So we have x values that are going all the way down the length of the beam. And then all we have to do over here is hit F3 or go over to solve table, and it'll populate the variables for all of the rows in this table for our load, shear, and moment diagram. So it calculates them. It says, oh, we have a potential unit problems. Okay, well, we can look in here, and we automatically got our shear, our load, shear, and moment diagram. As you can see, we got all these values. Those came from these equations here. Okay, so we defined our load here, which is our reaction force times the impulse function when A is 0 minus the distributed load, okay, as a when x goes from goes past A, it applies that step function. And then we have our other impulse function when A is equal to L. So all we have to do is set up these equations properly. So we set up our loading equation properly, and then we integrate it. Okay, we integrate these functions. Okay, so impulse goes to steps, steps goes to ramps, steps goes to ramps, ramp goes to parabolic, impulse goes to steps, step goes to ramp. All right, so then we can get our our load, shear, and moment diagrams. Now, if we want to plot these, we can go to our plot, and we have to pick an x-axis. We'll pick x as the x-axis, and then we can pick our load diagram as the y-axis. Then we'll go, say, from 0 to 40 in 5 tick intervals. Okay, and then, that's x40. So x only goes to 10. So then we'll actually okay. So then we see our load diagram. Okay, and it matches exactly what we expect for this problem. You can zoom in, it'll give you another plot. We don't go all the way up to 10. We actually need more. Okay. So when you zoom in, it makes another plot. I don't claim that this is the most user-friendly software, but you can see we have the shear diagram. You can't see super well, but this is the load for this problem. Okay. Okay, so I'm going to walk you through that again. We're going to fix the units too. So A is in inches. Okay, and then down here, actually, this is in SI units. So we can double click this and turn it into English units. Okay, and hit OK. I noticed some people put LBM in their homework, and that's pounds mass, and we're dealing with pounds force. Okay. And in this case, we're going to have LBF, which is pounds force, okay, times inches. Those are the units that we're actually dealing with here. The units of force are in LBF. And if you don't know which units to pick, instead of just blindly doing it, you can right-click here, and then it'll bring up the units for that system. In this case, I changed it to the English system, so we can use this here, and you can just paste it in, and it'll paste the value in. Okay. All right. So we have LBF. Our reaction forces are actually also in pounds force. So we can enter those in. Okay. All right. So if we try to solve this now, we have this x commented out because we want to use a parameter table. We'll see there's 8 equations and 9 variables. Okay. So it suggests some issues. So if we uncomment that, we want to find the value of the force. At any place we can do that. All right, and then we get all these parameters and make sure that they have the right inches, the right units. Okay, so it's just complaining about the units not being specified in the functions, which we are okay with. Okay, and now if we want to do a parameter table, let's say I made the mistake and I left this uncommented and I wanted to do a plot. So in order to do a plot, I need to come up here and do new parametric table, and pick the variables. Okay, so I want to pick X, M, I want to pick X, Q for the load, V for the shear, and N for the moment. Add those variables to my table. And then these are dependent variables here. So then if I enter this here, I want to start at a small number, I want to start at 0 and increase my X value by 0.01. And then I want to go all the way up to 10. I can do that. It'll populate those rows. We double check, make sure that it goes up to 10. And then I want to calculate these values. So if I hit F3, or I hit solve table, which is up here next to the solve, F2 is solve, F3 is solve table. Table 6 is the one that I'm trying to solve. I hit OK, and it says X1 is previously set to a value in the equations window. Okay, so these kind of little errors can be frustrating. All we have to do is comment this guy out, go back. Where did my table go? I think I lost my table. We'll bring our table back up. How do I... Okay, so here you can bring your table back up by parametric table. This is table 6. We can right click and go back, do our example. And then we've already added our X values, and then we can try to run it again. In this case, we hit F3. All right, we want to go through all of the X values. That's all it's asking it for. So it runs it. Okay, complains about the unit problems again, which we're not worried about. So this is pretty interesting. So we can see that our shear, our loading function is defined right at 0. And then right after that, we have our shear that starts. Okay, and then our shear goes and then all the way until some value when we have that distributed load that's a negative, that causes that negative drop, and it creates a negative shear. And then it goes all the way up to our reaction force, okay, which is equal and opposite to the force that's on that reaction. All right. So then, if we want to plot this data, we can. All right, and so we can come here to the plot, go to the plot window, and we can make X our x-axis, and we can plot all 3 of these on the y-axis. And let's make sure we get everybody. We'll make this minus, I think, minus 50 to 100 should be good. And what we want to do too is automatically update the table, the plots. The plots don't automatically update by default. And so if you change the values and you don't see your plots change, then you'll have to make sure that it says automatically update. Okay. So this is moment, load, and shear diagram, and then there's our expressions for the moment, load, and shear diagrams. And so if you go back to the example in the book, you can see here this is the loading diagram. Okay, so it goes from 0 to 18 in the load diagram. It's kind of hard to see it on the edges, on the ends here, but if we zoom in on the end, okay, we see that we go from 0 to 18. I mean 18 to 0 on the load diagram. Okay, there's 18. You can see the cursors down there. So it goes from 18 down to 0, just like we see in the load diagram, and then it stays, at 0. So that's our load diagram. And then over here we see that our shear, okay, starts at 18 right past 0. Okay, so if we look up here, it starting at 18, and then it has constant shear. And then it comes down all the way to 4, and then it begins to go, this is the shear is the red, it begins to go down in slope. Okay, so the shear stays at 18 until we get that applied distributed load. And you'll remember the beam loading function. There's the beam, there's the load that's applied. We got our reaction forces here and here. So we have our loading diagram here. We come all the way down to where this distributed load starts, and then it causes the shear to it causes a negative shear or negative slope, okay, because it's linearly decreasing as it goes along in the distance. And then we have our reaction force, which brings us back up to 0. And so you can see that here. Here's the 0 line, okay, that we have from here. You see that our reaction forces come back to 0. And then if we look at our moment diagram, okay, we start off at 0. We go up to our peak moment here, where the shear diagram crosses 0. Okay, somewhere, over here. Actually, move that over. So we have our peak moment, and we can see over here that this peak moment occurs right there at about 88, just like we see here for that loading function. Now, I want to reiterate the fact that all the work that we really had to do was to pick the right function based upon the condition in the load, and then integrate that function to the right next function. So impulse becomes steps, step becomes ramp, step becomes ramp, ramp becomes parabola, the parabolic functions or the parabola functions. Okay, so as long as we get our loading equation here done, then we're good to go. What's also very interesting to notice, we didn't have to do any solving of the equations. We didn't have to rewrite them. We didn't have to do any algebra. Okay, we just had to apply our knowledge properly. So EES goes ahead and solves those problems for us, and then we can actually do a parameter study and see how they vary over time. Okay, so now if you're thinking about like a design problem where we have to size a beam or size a shaft or whatever, and we have different loads on it, and we change the cross-sectional area, it's really nice to be able to have software to support you to see how all of the loads will automatically be updated. So that's why we're going through the effort to show you how to use EES to solve these problems. Okay, so this is an example. I've assigned some other examples. I'll upload this file so you can use it as a starting point, so that you can do the assigned homework for your problems. All right, so I hope you found this useful, and I hope you will go ahead and get started on the homework that'll be due next week with singularity functions, so that you can get your loading conditions. And once we have these loading conditions, then we can calculate the stresses. Once we know the stresses, we can look at the failure criteria, and we can make sure that we have a safe design. All right, you guys have a great weekend, and I will talk to you next week.